Hi, so welcome back to analog electronic circuits. So today we are revisiting MOSFET. In fact, it is continuation of the previous lecture. Previous day we have discussed about NMOS transistors, particularly NMOSFET, and today we will be going for P channel MOSFET, namely P type MOSFET. So, the overall plan what is as I said that we have discussed in the previous class about these 4 topics. So, these things already has been discussed, and today we are going to discuss about the similar kind of things, but for P type MOSFET. So, some of the things may be kind of repetition of whatever we have discussed about NMOS, but then we will try to compare the situation of NMOSFET and P MOSFET. So, that you should not get confused while you will be dealing with circuit containing N type as well as P type MOSFET. And then subsequently, we will be in case if time permits, then we will be covering some part of the numerical problems. So, to start with, let me go for the basic structure of the P MOSFET, keeping in mind that in MOSFET in as a background information. So, here the MOSFET for PMOS type I should say, where the channel it is it is supposed to be P type, and this is the cross sectional view of P type MOSFET. Just for your reference, I am also keeping the N channel MOSFET. So, I should say just for our reference, we are keeping N type MOSFET. And the basic difference here, if you see that the substrate or the body here, I should say body instead of calling substrate. So, this is N type, weakly doped N type, in comparison with P type body there for N MOSFET. And the 2 islands here, they are which are working as source or drain. They are P type islands and rather highly doped P type islands, and similar to in MOSFET, here also we do have the highly doped island for the body connection. In this case, the body is N type. So, we require N plus island, and so on top of that we do have the metal connection, and then we are getting the body terminal. And similar to in MOSFET, we do have the gate electrodes here, and just below that it is having the silicon dioxide. So, it is having silicon dioxide here, and then below that we do have the substrate or the body. And then in this case, to really create the channel, we have to see what kind of voltage you have to apply at the gate with respect to source, and then we will see that what other things are happening in detail. But this is what the cross sectional view. The oblique view on the other hand, the oblique view it is shown here, where this is the width of the gate, or I should say channel, and this is the length of the channel. They are the important parameters to define the behavior of the circuit, rather performance of the circuit. This is the oxide thickness T ox, that is also a critical parameter, and so this portion is of course it is substrate, and so and so. So, now so this is of course it is more idealistic cross sectional view, So, we have discussed for N type device what may be more realistic things, and also the top view. So, let us see for P MOSFET, while we do have P islands and then N type substrate, what may be the difference of the top view in comparison with N MOSFET. So, here so this is the cross sectional view of the P MOSFET, and this is the top view of the MOSFET. So, let us see what other things we do have. This is the gate electrode. So, this is gate electrode, and entire thing actually it is polysilicon. And then we do have the other rectangle here, which shows the boundary of the diffusion region. In fact, underneath this gate the diffusion is not happening, only this portion it is having the diffusion, and this portion is also having diffusion, and in this case those diffusions are basically creating the two islands, P types islands, P plus islands here, and this is also P plus islands. And you might have observed that the gate region, it is also not only this side, this side also it is getting extended, but then channel portion it remains the same as you have seen for the N MOSFET. So, the channel portion is here, and this is the spacing between the two islands we call length of the device, and this is the orthogonal direction of the current flow, or it is called width of the device. On the other hand, we do have the N plus island also, and this is the boundary of the other diffusion region, but this diffusion it is of N type. So, we can say N plus, and in fact, rest of the things here, they are weakly doped N type. And similar to as you have discussed for the N device, we do have the contact here. So, this portion is contact, this portion is contact, and so and so. So, these contacts are basically the substrate contacts, and then drain contacts, then the body contacts, and so and so. And then also we do have the gate contacts here, but this is not really in along this cross sectional view that we have discussed in the previous class. And on top of that there are different rectangular box here. So, if you see here, so this portion it is basically representing the metal 1. So, on top of this contact we do have the metal 1 here, we do have another metal 1 here, and so and so. So, this portion is metal, this portion is metal, and so and so. So, that is a little bit about the top view of the actual device. In fact, if you see rest of the things, it looks like it appears to be hanging, but actually here we do have the silicon dioxide, but then rest of the things is also having silicon dioxide. In fact, everywhere we do have the silicon dioxide that provides electrical isolation as well as the mechanical stability. And in fact, here also at the surface level also we do have the silicon dioxide, it is referred as field oxide, which isolates one device to the other on the surface. So, that is the, as I said, that more realistic view, but we may not be really going in detail of this structure again and again. Rather, we will be preferring to follow the simple cross sectional structure to explain the working principle of the circuit. In fact, this cross sectional view, it is more like cross sectional view along this axis, may call A dash, but you might be observing that along this axis this is not really getting cut, So, this portion of course, it is not getting cut. So, I should say rather I should draw this portion in dotted line for perfect engineering drawing. But anyway, so likewise probably you can make an attempt to draw the cross sectional view along this axis, say it may be called B dashed, okay, along the W, and you will be seeing that the gate is like it is having a texture like this, it is having up and down. So, this is the gate portion, gate electrode, and then you do have the contacts here, you do have this contact. So, that contact it is here, and then it is having the metal connection, I should use different color. Yeah. So, this is the gate connection, and underneath we do have the channel portion. So, we can see that here we do have the thin oxide. So, here we do have the thin oxide below of the gate region, but beyond this if you see beyond that this thin oxide is further getting extended like this. In fact, this portion it is also silicon dioxide, but actually beyond the channel region. So, you may say that this is the width of the channel, and so this is the edge of the channel, and this is the extension of the gate beyond the channel. Underneath we do have the filled oxide like this one. In fact, this structure I have not covered for in MOSFET, but it is there also it is similar. And for historical reason, this gate region earlier it was metal, but then as I say that because of better threshold voltage adjustment for n type and p type device, it has been observed that it is better to keep this as polysilicon because of the work function difference of the metal to substrate. So, anyway, I will not be going detail of that, but probably you can refer to any device course for that. Now, see how we bias this circuit. So, let us think about the biasing. So, primarily we will be covering the in MOSFET, P MOSFET, but just for our reference we are also keeping the NMOS structure. So, for your reference, if you see this is NMOS, and if you recall how we have biased it. For proper operation, gate is at higher potential by VGS, and most of the time we prefer to keep this body and source connected together, and then at the drain we do have another potential source we call VDS. So, for proper operation, VGS should be higher than something called threshold. VDS definitely it should be positive for the electron to flow from the source to drain. So, electrons are moving in this direction, and that results the current flow in this direction. Now, this we already have discussed in the previous part. Now, let us see how we bias the PMOS transistor on the other hand. Now, here at the gate we like to prefer to apply some voltage, so that the channel is supposed to be getting created, and we want to convert this channel from N type to P type. So, definitely we require to apply negative potential with respect to source as well as body, and because of the polarity the other way we may call this is VSG, and on the other hand, at the drain we can apply negative voltage, so that so anyway, I will discuss that. So, we call this is since this is source side, it is higher potential, we call this is VSD. And while you are applying this negative voltage here, it is expected that holes it will be coming into this channel region, and because of this VSD, it is offering lateral field, and this holes are moving from left to right. As a result, it produces a current in the same direction, and now this current, since it is flowing from source to drain, just to have proper convention of the positive current flow, we may call this is ISD. So, you can see the basic difference here, particularly the polarity. Here we call IDS, whereas for p type device, so p type MOSFET, we are calling this is ISD. So, likewise, if you see the polarity of the voltage here, based on that we are calling this VGS. On the other hand, this bias it is called VSG, and likewise instead of VDS we call this is VSD. And the current flow, of course, ISD for this case IDS it is flowing in this direction, and whereas ISD here it is flowing in this direction. Okay. Now, since the current flow as well as the polarity they are different, and for our convenience, it is better to keep the device orientation such that the higher potential terminal to be going upper side and lower side will be having lower potential. Namely, this side it will be pulled towards ground, and this may be pulled towards the supply, positive supply. So, a similar thing probably we can do here also, since this is a lower potential. So, probably we can pull it low and then we can pull it high like this one. So, let us see how we let us see how we reorient the device, so that it will be more convenient to place the device while we do have many circuits, while we do have many devices in the circuit. So, so what kind of reorientation shall we do? First thing is that we will flip the PMOS transistor, because here we do have lower potential and here we do have higher potential, and so source side, as I said, we can make it towards the ground, and drain side we can make it up. So, likewise, since we have flipped it, source side we have taken towards the right and drain towards the left, and we know that drain it will be at lower potential than the source. So, now here also we can rotate the device in the same way as we are rotating the NMOS device. So, this is of course NMOS device, and this is PMOS. So, first thing is we have flipped it compared to the previous diagram, and then we rotate it 90 degree. So, as we are showing here, so the body and source it is coming towards the ground, and drain it is going towards the positive supply. So, so here also, so the source and body it is going towards the positive supply, drain it is going towards the ground. So, basically we are reorienting, adjusting ourselves so that the device orientation it will be consistent in the circuit. Whenever we will be discussing with the circuit, normally we will be placing the device like this. In addition, here I am also showing the corresponding symbol of the devices. So, this is for the NMOS. So, this is MOSFET symbol, and this is PMOS symbol. And if you see here some conventions, if you have observed carefully that the source is having an arrow. In fact, this arrow it is consistent with the flow of the current IDS. So, you may recall that the current is flowing from drain to source IDS, though the electron is moving from left to right, but the current is flowing from top to down, basically drain to source. So, this arrow it is consistent with the flow of the current, and then we also have the body, though the body we are taking along this line, but for our convenience just we are showing like this. And in the biasing most of the time, unless otherwise it is stated, we may connect the source and body together. So, we may connect these two together. On the other hand, if you see the symbol of the PMOS, so here also we place an arrow, but if you see the polarity of the arrow, it is from source towards the drain. So, of course, that is also consistent with the actual current flow, and since the current is flowing from source to drain, so we call this is ISD. And as I said that this arrow it is consistent with the current flow. So, here also we do have the body, and unless otherwise it is stated, source and body may be connected, but we do have the flexibility. If you are really for some reason if you are not connecting it, you have to ensure that this junction it is not getting forward biased. In other words, the body should be at higher potential than the source for PMOS, and vice versa for NMOS. So, as long as we follow the that constraint, it is not a problem. But for this course, unless otherwise it is stated, we assume that body and source they are connected. Sometimes in some books we also place an arrow on the body connection, and for NMOS the arrow of the body connection it is in this direction from body towards the channel. This arrow it is really not consistent with the current flow, rather there is no current flow rather. In fact, we like to keep this arrow in a direction which is supposed to be representing the polarity of the diode getting formed between the channel and the substrate. So, the channel is N type and the substrate is P type. So, you can see that arrow of the body it is basically in this direction. So, this arrow on the body line it is consistent with that. Please do not get confused with the arrow on the body line and arrow on the source terminal. So, similarly here also the polarity of course, in this case it is P type channel, and the polarity of the this diode it will be from the channel towards the body. So, the polarity of or direction of this arrow it should be consistent with that, namely from channel to body. So, that is about the symbol, that is about the rotation and all. And now, let us see how we get the IV characteristic of the device. What is the working principle of the circuit, and then that will be helping us to really derive the expression of the current in terms of the terminal voltages. So, quickly let us apply the voltages here. So, what we said is that this is the channel, it is we have to make it P type. So, it should be at gate should be at lower potential than the source by VSG, and we have to apply VSD So, we do have the VSD here, which makes the drain side at lower potential. So, this is of course, we have to make the drain at lower potential with respect to source. So, that the current actually it is flowing in this direction, and also we said that the hole supposed to be flowing in the same direction. Now, what are the things are happening here? If the VSG, it is if you are making it more and more positive. So, what happens is that the majority carrier, namely electrons, they are departing the channel portion. So, which means that by this VSG we are forcing this electron to be moving away from the channel. As a result, it leaves behind positive ions there. So, let me use different color to represent that. So, it leaves behind the positive charges there, but they are the static ions. Of course, they do not participate for the current flow, but they are instead working like a depletion region. So, then if you further increase this voltage, namely if you make this gate further negative with respect to source, then the holes may be getting attracted from the substrate, maybe in the, they are minority carrier, but they will be attracted. In fact, if since we do have this island, holes it may be rather supplied from this island more, and as a result there will be a thin layer of the ions. I should say it is not ion, it is holes. So, there will be free holes. So, let me redraw the channel portion with the change of this voltage. So, if we further increase this VSG, so we are expecting that there will be holes just near the surface, and of course, there will be the static ions. As I said that they are not participating for the current flow, but they are basically neutralizing some part of this potential. So, now if we apply the voltage here at the drain with negative voltage here with respect to the source, and then the holes it starts moving in this direction. So, as a result there will be a current flow, and this current it is flowing from source to drain, and then it is going to the drain. So, this ISD it is flowing from source to drain. Now, before we go for this flowing, in fact, similar to NMOS, if VSG it reaches to a value, a critical value called threshold, and if the holes concentration here it is exactly equal to the electron concentration deep into the substrate, then we call that channel portion or the surface of the channel got converted from N type to P type, and their concentrations are exactly equal. So, you may say that the channel got inverted with this, and the channel got inverted to a critical level, where you may say that the channel concentration, channel strength and the substrate strength in terms of the carrier concentration, they become equal. And if you increase this VSG further, then of course, there will be more and more holes it will be getting accumulated in the surface, and of course, they will be contributing more towards the they will be rather helping this current to be flowing more. And of course, we are assuming that the body should be connected there. So, that is the basic working principle. Now, we will try to see what is the expression of this current ISD as function of this VSG and VSD. Okay. So, we are let us look into what other things are going to happen if we apply the voltage. Yep. So, quickly let me apply the voltage. So, we have, as I said, for our convenience we have rotated the device. So, let me apply this VSG Now, it is very convenient that the positive side of the potential source we are connecting towards the upper side, and this is VSG. Body is connected together, body is connected to the source, and then we do have the VSD, and the current it is flowing in this direction. So, let me use different color here. So, current it is flowing in this direction, and that is ISD, and we like to find what will be the expression of this ISD. So, as I said that this current, of course, it will be it depends on these two basic potentials, and also it depends on the size of the channel, namely the length. So, this is the dimension, this is length of the channel, and the orthogonal direction is the width W. So, it is function of that. In addition to that, it depends on the oxide thickness and then dielectric constant of the oxide, and then mobility of the holes. So, the expression of the current, in fact, it is let me so you may recall that for NMOS device we say that this is mu p, there it was mu n, and in this case it will be mu p epsilon oxide divided by thickness of the gate oxide multiplied by W by L, the aspect ratio of the channel, multiplied by VGS, and this VGS it is entire amount, it is really not contributing to the channel. Some part it is going to the in fact, I should write rather VSG, sorry, this should be VSG, and some part of it is going to convert or invert the channel. So, we may say that that part it is you have to subtract, and then this is what the VSG minus VTH, that is contributing towards the conductivity of the channel. And of course, based on the VSD, we do have the current flow due to this whatever the potential we are generating from source to drain. So, this is the expression of the current ISD, and this is, it looks like valid, but similar to the previous case. In fact, this expression it assumes that the conductivity of the source portion is a function of VSG minus VTH. But if you see the other end, and if you are applying VSD is positive, this end, the drain end, may not be having the same potential across this junction. As a result, we have to, if the VSD is significant compared to VSG minus VTH, then you have to apply probably different formula instead of just considering this one. And the trick is that instead of considering only VSG and VSG minus VTH, we also should consider VDG minus VTH. And this VDG, of course, it is function of VSG and VSD. So, if you take average of these two instead of considering VSG minus VTH, then we will be getting more more accurate expression, particularly when the VSD is higher. So, let us see what is the corresponding expression we will be getting there. So, for significant VSD, what we are expecting there, it is the expression of the current, it will be mu p into epsilon ox divided by T ox into W by L into VSG minus threshold voltage minus VSD similar to in MOS device multiplied by VSD. Only difference is that instead of VSG there it was VGS and instead of VSD it was VDS. Rest of the things it is similar. Of course, we do have the mu also, it is different, but we can think of it as just a constant. So, as long as we are very sure that okay, we have to get the correct polarity of the potential, and if it is consistent for the operation of the circuit, then it is not a problem. And this is valid as long as the channel is existing at this end. But then this is true only when the V dG it is higher than the threshold voltage. Okay. So, if V dG it is higher than threshold voltage, then only we will be having this channel. In fact, we can rearrange this or we can rewrite this expression of V dG in terms of VSG minus VSD. So, as long as this is higher than the VTH, then only we can say that this equation is valid. In fact, at the limiting case when these two are equal, this part and this part are equal, then you can say it, the pinch off it is happening, and at the limiting case the corresponding current it becomes so this portion it becomes this becomes VSG minus VTH square by 2, particularly when so we can say that under VSG minus VSD is equal to VTH. So, under this condition, we can write that this part it is like this and rest of the things it is coming there. So, if you see so if I consider it is as I said that V dG equals to VTH, the expression of the current it is mu p epsilon aux divided by T aux and W by L into VSG minus VTH square by 2. And if you increase this, so beyond this one, if you rather if you violate this condition, namely if you retain this VSG to a value, and then if you, of course, body is connected to the source, and if you increase this VSD beyond some point, particularly if you are violating this one, then the pinch off it will happen here, the channel will get tapered like this, and all these things it will happen, and then the corresponding current it will be practically remains the same as this one, but then of course, depending on the value of this VSD, the pinch off point it will be departing the drain, and as a result the effective channel length it will get shortened compared to the metallurgical or the otherwise initial length we are having. So, this length it is getting shortened here to L minus del L, as we have discussed earlier, and this del L it is of course, it depends on what is the VSD we do have beyond this critical value, and to capture this effect then we consider 1 plus corresponding lambda VSD part. Okay. So, to capture this effect we can say that so the expression of the current under this condition, namely whenever pinch off it is happening, then we can say that the current here it will be mu p epsilon aux divided by T aux, and W by L, maybe 2 we can take it here, and then we do have the V S G minus V T H. In fact, I should take mod. I'll explain why we are taking mod here whenever it comes to the situation, but for the time being let you assume that we are dealing with only the magnitude and this multiplied by V S D. In fact, we should write V S D instead of V S D, we should write V S D minus V S D sat, where V S D sat equals to V S G minus V T H. In fact, that is the value where the pinch off it is happening. So, V S D sat is basically the voltage at this point at the drain to source to drain, so that the pinch off it is just happening. But then most of the time we do ignore, instead of considering V S D minus V S D sat, we prefer to write only this V S D. So, unless otherwise it is stated, at least in this course we will be assuming that V S D minus V S D sat it is approximately equal to V S D. So, that basically summarizes the IV characteristic equation. Probably we already have said, can you make an attempt to write this summarize this expression. I will not be again repeating here, probably you can do this one, and then we will see the graphical interpretation of this one. So, let me take a break of 5 minutes and then we will get back to you to go for the graphical interpretation of the IV characteristic. Thank you.